Welcome back to EduHub Academia and the World of Physics course, part B of lecture number 3 about classical mechanics. We'll start by talking about the kinetic and potential energy. Kinetic energy is the energy that the object will have due to its motion at a certain velocity v. It depends on two factors, the mass of the object and its velocity, and you can calculate the kinetic energy by using the formula half times mass times square of the velocity of the object, and the unit is of course in joules. On the other hand, potential energy is that energy stored in an object either because of its position or its state. What do we mean by that? When it comes to position, we talk about gravitational potential energy. It is related to the position of an object at a certain height above a reference level. What do we mean by reference level? It's the level that has a gravitational potential energy equal to 0. For instance, if you take the ground as your reference level, then the potential energy of an object at that level on the ground is 0. If you pick it up and take it to a certain height above the ground, above the reference level, then it starts gaining gravitational potential energy calculated by the formula mass times gravitational acceleration times height, and of course if the height is 0, again potential energy is 0. While the elastic potential energy, which is related to the state, can be explained simply by looking at an elastic spring. If you compress or stretch the spring by a certain displacement delta x, you are storing elastic potential energy in that spring, and that energy is given by the formula half times the spring constant k times the displacement square. How do you know there is energy stored in the spring? Simply let go and the spring will go back to its original position or shape. Then we are certain that there was potential energy stored in that spring. A fundamental law in physics is the conservation of energy. Energy can never be destroyed, can never be created. It can only be transformed from one form into the other, and there are so many forms of energy, or it can be transferred to another object. For instance, if you look at this diagram, you can see an object at level A above the ground by height h. Because of its height, because of its position, it possesses now potential energy, gravitational potential energy. When it starts rolling down, potential energy starts to change into kinetic. At level B, at position B, it has both potential and kinetic, but the total is still the same as the original PE. And when the object reaches the ground level, remember, ground level energy, potential energy is 0. All of the energy of the object at level A will turn into kinetic energy at level C. Now, do we say that the object has lost its potential energy, original or initial potential energy? No, we don't say it lost. We say simply it turned into the form of kinetic energy. But in all cases, if there is no external force acting, like friction here, then the total energy will remain the same. Momentum, linear momentum, is something that the object possesses because of its motion. And it's given by the product of mass times velocity. It's a vector quantity, as you can see there. When no external force acts on the system of objects, then the total linear momentum remains the same, and we say it is conserved. Another type of motion is rotational motion, and as you can see in the picture, there's an object which is rotating around a certain axis. Sometimes this axis is imaginary axis, sometimes it's real physical axis you choose. The object will rotate around this axis, and then we don't talk about linear displacement or linear velocity or linear acceleration. We talk about angular displacement, angular velocity, and angular acceleration. These are new terms related to rotational motion. But an object cannot rotate by itself. It needs some force to act on it at a certain point to cause its rotation. So the force that can really produce rotation of an object has a torque, has a moment, has the ability to rotate an object. Think of the door. When you open a door, you are actually rotating the door around the hinges by applying a certain force on the handle. The distance between the handle, where you applied your force, and the perpendicular distance and the hinges, that distance will give you the maximum torque. And it's equal to the product of the force times the length or the distance between the point of application and the hinges, and we call it as you can see here, the lever arm, R. We are multiplying two vectors. So here we have cross product of vectors, and we end with a vector, which is called the torque or the tau. Its unit is Newton meter. Because we have rotation, because we have angular momentum, we talk about rotational or angular velocity. Now, angular velocity will mean that we have to talk about angular momentum. Angular momentum L can be calculated by the product of moment of inertia I times omega, which is the angular velocity. What is I? What is this moment of inertia? It is the tendencies, the measure of how much resistance an object will give to oppose the rotation. It's called moment of inertia. Every object will try to oppose, to stop, to resist any tendency to cause its motion, including rotation. Now, angular momentum is conserved in the absence of external torque. Notice here, we don't say in the absence of external forces that's related to linear momentum. But in angular momentum, we talk about conservation only in the absence of external torque, meaning that the total angular momentum of a rotating object will remain the same. Thank you very much. I look forward to meeting you next time, and please remember to subscribe below.